Much better. Not really.
Aloha. If you can hear me, the Zoom room is the wrong link that was provided.
Hey, Amber, I can hear you.
Sorry, I was trying to talk to the people who are in the other Zoom room with me.
Okay.
Yeah, so I sent them over here. I gave them a
Okay.
link.
Okay, great. Okay, thank you, Amber.
Yeah. Sorry, I forgot I was on unmute.
It gets complicated. Okay, so for everybody else who's here, good evening. My name is Brian Lemaux. I'm a scientist at the Gemini-N Observatory on the Big Island of Hawaii. So one of the other telescopes that are on the summit of Maunakea. I'm observing tonight on the Keck I telescope with the instrument Mossfire. So I've shared my screen with you. And so hopefully people can see a little bit about what we're doing tonight with our observations. The other person who is observing with me this evening is Patricia Bolan, and she's at University of California, Davis. So I'm actually located in my home office on the Big Island of Hawaii. Patty was brave enough to go to the actual department at the Physics and Astronomy department. So you can see that nice cosmology banner in her background. So this is our remote observing room. So this allows Patty to observe with Keck and other telescopes around the world from our, well, what used to be my department, which is now my alma mater. And so she's controlling the telescope. She's doing most of the observations. I'm along for the ride to ride some photons with her. We have another astronomer that is going to come on later from the University of California, Santa Cruz, Raja GuhaThakurta, and he's the person who actually started this Shadow the Scientist program. So he should be on shortly. You may have gotten some messages about some inclement weather on the summit of Maunakea. It turns out those were a little bit overblown. So Maunakea is a very special place. What happens 1 hour is not necessarily what's going to happen the next hour. And so we thought some ice, snow, clouds might prevent us from observing this evening, but very thankfully, that's not the case. And so we are open up to the universe, and we are actually getting photons from the deep universe right now. So the other people that are joining us from Keck are John, who is actually controlling the telescope, so we rely on him a lot to move where we need to move, and we're actually on the bottom end of the telescope. So John points the telescope where it needs to go, and then we're kind of on the instrument detector side at the bottom of the telescope. So the photons come through the telescope and then hit the detector, and that's what we're in charge of. So Patty and I are in charge of. And then we have Chen Xu, who is our support astronomer for this evening. I guess Chen Xu, you're joining us from Waimea, from your home in Waimea?
Yeah, that's right. Yeah, we also work remotely. Yeah,
so actually nobody here is, this is my first time actually observing with Keck. Nobody here is on the summit. So that's interesting. So we're all scattered across the Big Island or in California, but not at 14,000 feet observing tonight, which is nice because you can make dinner and coffee and not be cold and stuff. We are taking observations right now, as I said. And so I think we could maybe start off, Patty, with, if you're comfortable now. So I think we've gotten to a point, correct me if I'm wrong, that we're feeling pretty good about what we're doing. That we are in the right location. So just to give people context, we actually started off the night, we focused the telescope. So we decided that there wasn't much ice on the dome, which was great. There was actually somebody up on the summit checking to make sure nothing fell into the dome when the dome opening was retracted. So that was good, and not a lot of clouds up at Maunakea right now. So we went to our first science target, and we focused the mirror. And so we're all focused. Everything looks good from our perspective, and we've trained Keck on the location that we want. So the galaxy that we're interested in, it's actually galaxies. But we have one galaxy in particular that's really, really important that we're looking at right now. And probably Patty will explain a little bit about that when she shows us some slides in a second. So we're taking a spectra of these galaxies. So you can see in the screen that I'm sharing here, actually, so first we had to make sure that we were pointing exactly where we thought we were pointing. So the kind of peak things here on the right hand side of this screen, these were all stars that we used to align the telescope, so to make sure we were pointing precisely where we needed to point. And we need to do that, so like when you take an image of a part of the sky, you don't need to be so precise. You need to be very precise, but you can be, a little bit off, and by a little bit off, I mean like, fractions of a fingernail held at arm's length. So, so still, pretty precise, but not crazy precise. But when we're taking spectroscopy, which means we create a slit and we pipe the light of a galaxy or a star through that slit, and then we have a prism or something like it on the other side of that slit that disperses the light. So like in Pink Floyd's Dark Side of the Moon album. So you have the white light that goes through the prism, and you have all of the constituent colors of the rainbow that come out. And so, so we pipe the light through the slit, hits a prism or something like it, and then goes on our detector, just like a camera, except we're observing the infrared, so it's a little bit different, but more or less just like a iPhone camera or something like that. And we get all the constituent colors of the galaxies that we're interested in theory. That's the hope anyways. And so this slit is very, very narrow. It's fractions of a fraction of a fingernail held at arm's length. And so we have to be really, really, really precise about where we point the telescope. So we're feeling very comfortable now that we're pointing in the right place. And we're now opening up the shutter of our instrument to point in this location and to collect photons at this location, with the hopes that we will get a few photons from the very distant universe that will tell us something about the galaxy.
Exposure complete.
About the galaxy that we're interested in. So I can stop sharing now. And Raja, you joined us. Wonderful.
Hi there. Sorry I'm late joining.
Not at all. Raja, would you mind introducing yourself before we're going to actually have Patty do a little bit of a presentation, since we're in a kind of comfortable place right now?
I think I've met Patty before, and I've certainly met you before, Amber. And let's see, Brian, I know for a very long time. Let's see, who else do I recognize on the call? Vicky, of course. So I apologize that if you already know me and I'm introducing myself. I wanted to check, Chunsu, were you in Tucson before coming to out to Keck?
Yeah, that's me. Hey, I haven't seen you for a long time. How are you doing?
I haven't seen you for a while. Okay, because I recognize the name, but we haven't, I don't know if we've met in person. We've met on Zoom before. And we met in person years ago at Leiden, at the Andromeda meeting.
When you were in Tucson for the board meeting, right?
For the Aura board meeting, that's right. I stopped by, I stopped by Monica's office then.
Right.
So you're now in Hawaii?
Yeah, we also met in Hawaii when you were in Waikoloa Village for the Subaru meeting.
Say that again, sorry?
So I think we met again when you were in Waikoloa Village for the Subaru meeting.
Ah, for the Subaru meeting. Yes, yes,
Yeah,
yes.
it was shortly before the pandemic, right?
Just before the pandemic, that's right.
Right.
That's right. Well, welcome to Hawaii.
Yeah.
So I'm Raja. I'm a professor at the University of California, Santa Cruz, and I've been there for 28 years, and I've been using Keck for much of that time, since 95 actually, so 27 of those 28 years. And our research group decided that when we went to pajama mode observing because of the pandemic, that opening up the Zoom link to people outside our team, specifically non-astronomers outside our team, would be a great way to give people a sense of how astronomy gets done. What are the conditions right now on Maunakea?
They are amazingly wonderful.
Good.
Yeah, it was really, really bad. I think you might have seen the webcam screenshot that I sent out.
Yeah, I saw that.
5 hours ago, maybe. So it looked very, very dire. You could see a little bit of blue in the background of that picture if you look closely. And that little bit of blue persisted. So we are looking really good. We have 0.5 arc second seeing in JPN, and clouds look thin.
That's wonderful.
Amber, I didn't recognize you when you came on, but do you want to introduce yourself real quickly before Patty shows off what we're doing for tonight?
Sure. Real quick, my name's Amber Mai Hong. I'm an avionics engineer with the Hawaii Spaceflight Lab, and I am one of the board of directors of Ohana Kilohoku, which is a Native Hawaiian group that supports astronomy and space science in Hawaii. Thank you so much for the opportunity.
Thank you, Amber. Cool. So Patty, do you want to tell us about what we're doing tonight? Teach us some things about what's going on up there?
Yeah.
What
Yeah,
we're
I'll just
staring
give you guys, just a brief overview of what we're actually looking at tonight. Yeah, like Brian said before, I'm a grad student at Davis. Running the observations from our remote observing room in the physics building, which is fun. I brought my dog buddy with me for some company. So, but yeah, I have just a few little slides just for some visuals to show you what we're looking at.
It's going to be a long night, Patty, because you're 3 hours ahead of us. So when the sun comes up in California, you're still observing nighttime photons in Hawaii. And I'm actually going to abandon you at 3 o'clock Hawaii time. So you're going to be all alone. Sorry to say.
Yeah, that's why it's key to have the dog. So.
Totally, yeah.
But yeah, that's the worst part is you can see the sunrise here in California and we're still exposing on the telescope when you just want to go.
It's even worse than that because parking enforcement comes at about 7:30. And so you have to run out and check your car and make sure that nobody's giving you a ticket when you're observing on one of the world's biggest telescopes. That doesn't get you out of a ticket, unfortunately.
No, they don't care. And also people start to come in for work in the morning and you're still here having been up all night.
Then they want to have high level scientific conversations with you. Like, oh, you're here. Oh, you showed up early. Okay, great. Let's talk.
No, never do that. Here we go. All right, cool. So yeah, I'll just briefly go over what we're looking at today. The general overview is that we're looking at galaxies that were formed within the first billion years of the Big Bang. So that means the universe is less than 10% of its current age, because right now it's almost 14 billion years old. So we're looking at basically the first galaxies that ever formed in the universe. It's really hard to do because number one, they're really, really far away, right? Because the universe, is constantly expanding outward in every direction. So they're even flying away from us at every second and getting further and further. So the light we get from them is very faint. And also, since they're some of the first galaxies that were forming, they're still quite young. I like to call them little baby galaxies. And they haven't had time to evolve into, the beautiful spiral structure galaxies that we see today and to build up mass and get brighter and brighter. So we're looking at these little faint galaxies really far away. So the main theme of all the observations that I've been doing since grad school is you go on one field, one target, and you have to observe on that for hours and hours at a time in order to get any useful data out of it, just because they're so faint. Telescopes are just like big cameras, right? So it's just like taking a camera and holding up for 10 hours straight. But we cut it up into little 2-minute exposures and then add those all together at the end. Just a brief overview of why we're looking at this, when in cosmic history we're actually looking at. So this is just a brief overview of cosmic history, where on the left we have the start of everything, the Big Bang. We had all these, particles just floating around in this cosmic soup. And then things began to expand. And as the universe expanded, things started to cool down until eventually the temperature got low enough that all those free protons and electrons and neutrons and things floating around could combine into atoms. So that's the process called recombination here. And then eventually what happened in the part of the universe that we're looking at is, you can see here, called reionization. So most of the universe is composed of hydrogen, which is one proton in the atom. It can have an electron around it or not. And the process of reionization is when all of that hydrogen, which was neutral, aka one proton and one electron, so electrically neutral, all those neutral hydrogen atoms became ionized. So that means that energetic photons or something was coming in and imparting enough energy on those electrons that was able to strip them from the protons. And then you'd separated hydrogen atoms, which are just protons, and free electrons floating around. So that whole process is called reionization, basically when all the neutral hydrogen in the universe became ionized. And this is still kind of a big mystery in astronomy. There are a lot of questions surrounding the era. So a couple of things I'm super interested in are what specifically caused reionization, right? You had to have some kind of light source that was emitting all of these photons in order to energize the electrons and ionize the hydrogen. Another big mystery that we've been thinking about is the timeline of reionization. Looking so far back, it's kind of hard to tell exactly when it actually onset, and figuring out how quickly it happened, whether it's a really rapid thing within, you know, a few 100 million years, which on cosmic time scales is actually a very short amount of time, or if it was kind of more elongated. And that also depends on the kind of sources that were emitting the photons causing the ionizing. So yeah, those are actually, let me skip to this before I get to the next one. So those are basically the main questions we're trying to answer, and looking at these galaxies. Our big science goals are we're trying to figure out properties of these first galaxies we're looking at. And Brian was explaining that we're doing spectroscopy. So we're looking for what are called emission lines, which is basically a light that's emitted at one specific wavelength, and that's due to I'm trying to think of a good way to say this, transitions in the atom. Basically, if you have a proton, you have electrons surrounding it at different energy levels. And when they jump between different energy levels, they can let out light at very specific wavelengths. So we're trying to track that light at those very specific wavelengths, and that can give us a lot of information as to what's happening inside the galaxy, if we can get that light. And then the other main thing that we want to see is what I was just talking about. What impact did these galaxies have on the universe? How much did they contribute to reionization? And yeah, how exactly did reionization progress? And there's pretty good evidence now that the galaxies we're looking at, these young faint ones, probably had a pretty big role in reionization, which is why we're targeting them to get more information. And then a cool little thing that could happen sometimes, I haven't found a galaxy, is just sometimes you can find a new galaxy that you didn't know was there before, but that's usually with imaging.
What?
Yeah.
Did you hear anything of what I said?
Yeah, I heard it all.
Okay, the meeting is over.
Okay.
I have a thing with UH
that.
astronomy. Okay.
So it
Sorry,
started.
Oh, it started at 7.
I'll mute the audio.
Okay.
I think that was just a crosstalk or something like that, Patty.
Yeah.
Patty, could you tell us a little bit about what the picture is that you showed? Like, I think it's the same picture in the background of the last slide.
Yeah.
Yeah,
Yeah.
that's a cool looking picture. What is that?
Yeah, exactly. So this is what's called a lensing cluster. So basically galaxies, right, are collections of stars and dust and dark matter, which we still don't know what that is. But all galaxies can also gravitationally clump together in what's called a galaxy cluster. And one really cool feature of this that helps us a lot with our observations is that it causes this phenomenon called gravitational lensing, which is basically where, if you can see in this picture here, you'll have this central mass of your galaxy cluster. And if you have, so basically we have galaxies we want to see that are behind that cluster. And what the lensing cluster does is it bends and magnifies the light around that galaxy cluster so that we can see things behind it brighter than they actually are. So like this feature here, if you guys can see my mouse here, this arc here, that's a key feature of gravitational lensing, where this is originally just one object, but because of the distortion of light around that cluster, it bends that light out into an arc. So this is actually really helpful for the galaxies we're looking at because they're really faint, as I was saying. And what this gravitational lensing does is it magnifies that light for us. So it acts as a magnifying glass, and we can actually see them a lot brighter than they would be without this lensing cluster there. So basically every galaxy that we're looking at is magnified by a large lensing cluster. So we have a couple different big projects that are working on this that used Hubble Space Telescope imaging to identify these clusters and figure out which images in this picture here belong to high redshift or really, really far away galaxies, the one that we're looking at. And yeah, so we pretty much look only at these lensing cluster fields because it allows us to see fainter galaxies due to the magnification of the light. So, yeah.
And so the magnification factors that we have, so like the multiplication factor of the brightness of the galaxy. So like you have a galaxy that's like, you know, a 60 watt bulb or whatever. And so the magnifications that we're looking at, well, I guess the one that we're looking at now is only magnified at 1.2 times. Is that right, Patty? So it's actually not so much magnification.
It's not too much.
Yeah. And so, but some of the galaxies that we look at are magnified, like, so in that case, 1.2 would be, you know, a 72 watt bulb instead. So not that big of a change. But sometimes we look at magnification factors of like 100 to 200. So, you know, 6,000 watt or, you know, 12,000 watt bulbs. So much, much brighter. And so we're looking really, really distant. And we're using one of the biggest telescopes on Earth, and we still need help. We still need help for magnification from these lensing clusters to be able to pick up the kind of objects that we're looking at. And even then, we need to stare at these things for 5, 10, 15 hours just to be able to see a few photons that indicate something that we're interested in.
Mm-hmm. Yeah, and there's a question in the chat, a really good one from Zagnik. How can we study the correct morphology of such galaxies which are lensed? Galaxies near edges look bent and distorted post magnification. Yeah, that's a really good question, and that's a whole other field that people work on called just lensing, or I'm like blanking on the word now.
The reconstruction.
Lens mapping.
Yeah, lens mapping. Yeah, like
okay, yeah.
The source, it's source reconstruction, basically. That's the technical term, but it's like it's basically unbending it and distorting the arc there. So like you have a really good example of an arc in this picture in Abell 370, not coincidentally, since it's one of the greatest magnifying clusters. But yeah, so that's exactly that, right? It's basically taking that and making a galaxy out of that. And so there are people at Davis, and that's not so much something that we do, but like Tucker Jones at Davis does this kind of thing. So and so does Chris Bosnott, trying to take this. So you have to essentially, I'm not a lensing expert at all, and Patty nor you, so we're looking behind the cluster trying to figure out some things. But yeah, so there's people. So this magnification factor that I talked about, this 1.2 or this 100, 200, this is given to us by people that are really good at trying to model the mass of a cluster. So they use you could use the velocity of the particles. So the particles in this case.
1 scoop of medicated food, period. Everybody else gets 2 scoops.
Yeah, so you can use the velocity of the particles, and the particles in this case would be the galaxies themselves. So you see the galaxies, you can actually measure the velocity of the galaxies, and that tells you something about the amount of mass that's there. And so you can kind of construct a mass model, and with the mass is what's doing the lensing. And so you can do a smooth model where you have just kind of a cluster mass, and it's fairly, you know, more or less a sphere or an ellipsoid, like a American football shape. But then you see all these galaxies that are in here. All these red big galaxies are part of the cluster, and so they also distort things. And so, like for example, the one that Patty just pointed to, that's actually contributing to the arc that's there. So you can see even some weird non-spherical shape to that arc. So it's not kind of tangential, or it doesn't follow a nice simple curve. And that's because there's perturbing mass. So other little tiny, with respect to the cluster galaxies, these are actually super massive, more than the Milky Way. But these things perturb the light coming through, and so you get finer order distortions coming from the galaxies themselves. So people are really good at trying to model this mass and then give us a model so that we can say, aha, that galaxy that we're looking at is magnified 50 times. And so, then we can do the kind of astrophysics that we want to do. And so they can use that same technique to reconstruct the morphology. And it's messy, and it's not something that that's always believed, because you have to get really fine order corrections for this. But it's possible to do this if you have enough data. And actually, one of the things that Patty didn't mention is that, so we're taking observations of specific galaxies really, really far away. And those are our primary targets of interest. Those are the things that we really want to be able to see. But we actually have, because this is what's called a multi-object spectrometer, we actually have about 30 slits total that we can observe with. And so, of course, if we only have a couple galaxies, maybe 1 or 2 galaxies in the background that we're really, really interested in, that leaves us with 29 or 28 other slits that we can look at galaxies with. And so we usually choose galaxies that are in the foreground that are going to help us map the mass a little bit better. So these red bright galaxies, we put them on the other slits. We point the slits at them so that we can determine how far away they are. We can determine their velocities. We can determine their compositions. We can even get internal velocities of the galaxies, so that can help us model the mass of the galaxies themselves.
Exposure complete.
Yeah, thank you. Yeah, exactly. So yeah, it's a little more info on how we see what we're looking at. Yeah, cool. Oh yeah, I just like have some comparison images of what we're looking at versus what you might think of when you see galaxies. So these are all fully formed spiral galaxies. Like the Milky Way is like 10 billion years old. And it takes a lot of time for galaxies to accrue enough mass because they grow bigger and bigger. Well, it's a little more complicated for them than that, but it takes time for them to get big and bright. And what we're actually looking at with these galaxies is, these tiny little blobs that are far away. This guy's an image of like the furthest known galaxy at like just a few 100,000 years after the Big Bang. And this is just an example of one of the galaxies on our mask that we're going to be looking at later in the night. So they're not these big, beautiful spirals at this point. They're still young little baby, just tiny blobs. So we're really lucky if we could, collect any photons out of them. But yeah, so
Patty, in that top picture there, sorry to interrupt, but the top picture there, that yellow thing that's running across, I guess that's our slit that we're observing with the instrument. And so, like, just to give people a size of the scale there, so this is a 0.7 arc second slit. That's the technical term, right? Okay, so 0.7 arc seconds. So that's like 1/5000th of a fingernail held at arm's length. So if you like look up at the sky, you hold your arm all the way out, you close one eye, and you have your fingernail, and your fingernail already like not that large on the sky. And then imagine dividing that into 5,000 parts. And that's the size of these galaxies. So if anybody's ever seen Andromeda, like through a telescope or even naked eye, it's pretty big. Like apparently on the sky, it's fairly big. And Raja spends a lot of time actually observing Andromeda with Keck, although he goes way, way, way out. So Raja can tell you that Andromeda is much bigger than it appears. But yeah, so that's a fairly large part of it's bigger than a fingernail on the sky for sure. And these things we're looking at are 1/5000th of a fingernail or smaller.
Exactly.
So crazy small.
Right.
Really hard to find.
Yeah, which is why we need a 10-meter telescope like Keck, at least ground-based, when we have to go through Earth's atmosphere in order to collect all the light that we can from tiny little guys. Sweet. So yeah, like Brian mentioned before, we are exposing on what's called a multi-object spectrometer. So I'm just I have like a brief little overview of the different steps that we're taking in order to get the data that we actually want from these galaxies. So this kind of ties back to what we were just looking at with this little, yellow bar here that shows us our slit. So this is just an image of the full slit mask. And this is something that we observed a couple months ago in January. We looked at this mask. So basically this little box here where you can see all the galaxies in there, that's the Hubble image that we're looking at. So that's where we get basically all the information to figure out which really far away galaxies we want to look at. We take images with Hubble and multiple different filters. And then we can figure out based on the light we get in all those different filters, which galaxies are likely to be these really far away first galaxies that we want to look at. And those are the ones we follow up on Keck with spectroscopy in order to try and get emission lines. So yeah, like Brian was saying, MOSFIRE, the instrument we're using now, multi-object spectrograph. So basically every little blue text and yellow box you see here is a different slit or a different galaxy or star that we're going to be focusing on. And you'll also notice that some of them are kind of covered up of 5 little red boxes. So that's when we were looking before at the original screen, those 5 alignment stars that we use to make sure that we're just super precisely on target. You look at 5 different stars because they have, they're like perfect circles. So you can fit their peaks really easily and then make sure that you're perfectly aligned to actually look at our high priority far away sources. So what we usually do in the beginning of the night in the afternoon, we couldn't today because we were in what's called foul weather mode, which means we couldn't put the telescope at the angle we needed to get calibrations. So I'm gonna have to stay back in the morning and do calibrations then for all of the masks we're looking at. But yeah, basically what calibrations are is you're just factoring out effects that the detector or the telescope has, like any inconsistencies between different spots in the detector. You can divide all of those out so that your data is as clean as it can be without taking into account those extra noise factors. So it's usually what we would have done at the beginning of the night, but you can also do it at the end of the night. So we'll just have to do that this time.
Patty, I'm just going to interrupt
yeah.
for a sec. So
Yeah.
we are still taking observations, and I just want to let you know that I'm looking at the observations. Everything looks fine.
Good.
And
Okay,
it looks like the signal is holding steady on the objects that we have traces for. So we have, I don't know, maybe 8 minutes or so before we have to do anything else. So
Yeah,
just so you know.
okay. Yeah, and this should be all set up to repeat because we should be able to get 25 to 28 repeats on this, and we just did 12. So I'll just run another 12 once this is done.
And I'm looking at, if you want to stop sharing actually for a sec, I can show what I'm looking at right now.
Yeah.
So can you see that?
Mhm.
Yeah, so these are the Gemini cloud cams. So Gemini is the observatory that I work for. And there's these really, really light sensitive cameras that we have outside of our telescope. And oh gosh, I don't know if this is Keck. So can you see my cursor? All right. So looking north, so this is looking north on the summit of Maunakea, and you can see that there's snow up there. So that was what we were worried about earlier today. But I think this is Keck II. So this is not us. Keck II is on the towards the east. So this Keck II. So we're just to the left of this, but it is absolutely gorgeous out. So we can see a little bit of bands in the helo cam. You can actually see some gravity waves in the upper atmosphere, but it's just light cirrus. That's it. Everything else looks absolutely gorgeous. So we are doing better than we deserve right now by the forecast. Okay, sorry.
Yeah,
I just wanted to interject.
Open it all. So
Yeah, totally. All right, I'll stop sharing and.
oh yeah, you're good. Sweet. Yeah, cool. Okay, so you might have seen on the screen earlier, I know when we first started, Brian was sharing our telescope control windows. But basically, so like I said, we're exposing for hours at a time. We do it in 2-minute chunks. So we take 2-minute exposures and then read out, and then like what we were just talking about, that everything looks good. This is the exposure that we actually see. So basically each of these bands here, you can see how there's kind of a disconnect between different slits. So this is vertically, you're looking at all of our different slits. There should be 30 something of them, I believe. And the one feature that's key to look at is, if you can see where I'm pointing now, there's this horizontal bright line here. So that's a star that we put on one of the slits, and that's used so that we can track in real time and make sure that we see that signal from the star. And that helps us, you know, gives us peace of mind that we're still looking at the right thing, that we haven't gone off target or anything. So we always put a slit or a star on one of the slits so that we can track in real time and say, okay, that signal's still there, which is what Brian was just telling me. He's like, okay, everything looks good, because we still have the signal from the star, and maybe some other bright objects on our mask that we can see. But yeah, so basically, once we take all these frames, in order to get any signal from our faint sources that we want to look at, we have to combine everything together along with our calibrations and basically co-add everything up to see if we got enough signal from the actual high redshift things that we're looking at. So this is an example of a reduced mask after it's gone through all. So reduction is the next stage after you've taken all of your images. There are lots of different pipelines or software that you put all your images into, and it does all the hard work for you. And basically gives you this reduced mask where it combines all of those hours of data you took, takes out the calibration, or, you know, divides out the effects of the detector that you got from the calibrations, so that you can actually see if you can see any bright lines for what you're looking at. So remember this horizontal line here from this star, once we reduce it, it becomes this really, really bright line here, because now this is combined. I think this was 5 hours worth of data. So we saw this brightness of the line after 2 minutes. And once we combine all 5 hours, it becomes this bright, right? So yeah, basically all these horizontal bands that you see here, those are going to be the brightest objects we have on our masks. And yeah, if an object is bright enough, you'll see what this is called continuum, which is basically just photons that are being emitted in every single wavelength across a whole spectrum. So just to give a little more context, I should put axes on here, but in the horizontal direction, or the x-axis, we're splitting everything up by wavelength. So the light's going through a slit and it's being dispersed over all the wavelengths in different colors of the rainbow. We're actually looking in infrared, so redder than the rainbow. So when you see a bright line across all wavelengths, that's what's called continuum, where you just have photons that are being emitted energetically at all different wavelengths. And what we're actually, yeah.
Quick question. So why doesn't it look like blue through red on the screen here? If it's like kind of like the normal way that we would think about like a prism or something like that, we would see things as like being blue through red, but here it just looks like a, I don't know, gray, white kind of bland nothing. So
if I'm understanding what you're looking for here, I think it's that.
No, I'm actually, yeah, I don't know. It's sad that we don't actually represent this. Is that right?
Yeah, that's true. I mean, we probably could if you just applied a color gradient to it,
Totally,
right?
Yeah.
Yeah, that would be cool.
But part of it is, this science doesn't get done visually. What we care about is not the visual color. First of all, it's in the infrared. The eye wouldn't even be able to see it. So there's no good mapping. But secondly, it's really the numerical value of the wavelength or frequency that figures into all calculations. So instead of coloring it, what you do is you do some kind of mapping where you go from X coordinate to wavelength, and that happens sort of through this reduction process that you were talking about, Patty. That's my take on. I mean, there's no use in putting color here, right? Because the colors would not be accurate because this is the infrared part that the eye can't even see. But even if it were in the visible part of the spectrum, you don't learn anything by putting colors onto that. You don't learn anything in real time by putting mapping colors onto the wavelengths.
Yeah. So for us, we're so used to looking at these and so used to thinking them in terms of numerical values. And, we have, for us, when we look at something like this, it's completely superfluous to how we visually represent it, because it's really just mathematics at that point. But anytime, we show off something like this and then we think about it being a prism, it looks very strange because there is no color gradient here. But in fact, the data array, the thing that we get out of this is information at every single one of those pixel values, every single one of those locations along the x-axis. We have a value of that wavelength. And so that is the value that we plug into whatever equation that we're going to be using, and determine the location of the emission of the galaxy that we're interested in.
Yeah, that's a really good point. I never even think about that because I never really dealt with optical data at all. So yeah, that's cool.
So I was looking at some spectra earlier today between sort of the red part of the spectrum, so sort of the end of the rainbow and the beginning of the infrared. So basically working between about 650 nanometers and about 920 nanometers, so 650 to 920. And we map red to the beginning of the infrared into 8,000 colors. And my eye, at least, has even if you were mapping orange to red into 8,000 colors, my eye doesn't have the kind of color resolution to be able to tell them apart. Whereas here, their numbers are distinctly different from one pixel to the next by a measurable amount. My brain can make sense of that by looking at a set of numbers, but it can't make sense of the colors.
Yeah, that's a really good point.
Exposure complete.
All right, I'm just going to keep an eye on this because we just have 2 more minutes before we have to restart.
I can do it, Patty, no worries.
Oh, okay, thank you.
You want to do, shall we do, you think, I'm going to do like 7 and we'll kind of see where we are at that point.
Yeah.
13 would be kind of the end of our track on this target. Yeah.
Mm-hmm. Yeah.
Okay. So we'll do 7 and kind of see where we are.
Sweet, perfect. Cool. Okay, yeah. So yes, so this is what it looks like when everything's reduced in all your different slits. So for our bright objects, you get continuum, but what we're actually looking for is just this tiny little blip. Just this, so this is from a nearby galaxy, not as far as away as the ones we're looking at. If we ever got a signal this bright, we'd be super, super stoked, and that would never happen.
Be
so
fair though, Patty, come on, this is still 10 billion light years away. This is, I'm guessing,
yeah,
this is H beta or O3. I even actually remember talking about this galaxy, maybe. So
yeah, this is the one.
This is okay. This is the one. Yeah, it looked familiar to me. I've seen a lot of those kind of galaxies, and yeah, so this is 9 to 11 billion light years away. So nearby in terms of,
yeah,
I guess what we're looking
biased
for, but still, 80% of the way to the edge of the observable universe. So it's still very, very far away. But I agree that this is an amazing example, and if we found something like this for the galaxies that we're looking at in really, really deep space, we would be incredibly happy.
Yeah,
you would be incredibly happy. You wouldn't have to do all the stress tests that you normally do.
I know, yeah, it'd just be easy. Yeah, but yeah, these are the signatures we're looking at. So once again, this is at a very specific wavelength because the light comes from an electron that jumped down an energy level in its atom. So it emits light at the energy of that exact gap that it jumped down from, which is how we get emission lines. So yeah, that's why you have this tiny little blip right here. And you'll notice these black spots on top and on bottom. That comes from what's called the dither pattern that we use for Mossfire. So because we're looking through the atmosphere, we have to take into account that the atmosphere is really bright. So remember this thing here, all these vertical white lines here are from molecules and atoms in the atmosphere because they also emit and absorb light at defined wavelengths. So the dither pattern we use is basically, you know, how I said we're taking 2-minute exposures. For every other exposure, we bump the telescope up or down a tiny little amount, and that helps us to get rid of the background noise from the atmosphere. So these two black dots on top and on bottom are traces from that dither pattern. So basically when we, when we do the reduction, you'll get these little shadows here, and that gives you a good idea that the line that you're looking at is real. Because a lot of times in the stuff that I'm looking at, the signals aren't this bright. You get something that maybe might look for a signal or look like a signal. And something that's really helpful in determining if it's real or not is if you see these black dots at the exact same distance on top and on bottom of the actual signal. And that's a good indication that it might be a real emission line. So that's basically the ultimate goal of what we're doing tonight, is we have 5 or 6 galaxies per mask that are high redshift, or the really far away first galaxies that we're looking at. And once we take all the data over hours and we do the reduction, I go through and I scan the slits that our high priority targets are on and look for these tiny little emission lines, these little bright spots. And I just threw this slide together while Brian was talking in the beginning, talking about the galaxy that we're looking at now that we're super excited about. So it's called DP7, Dichromatic Primeval Galaxy at redshift 7. And redshift, I don't know if I introduced this at all yet. Redshift is just basically a way to measure how far back we're looking in time. Because when you're looking at things far away, it's like a time machine because it takes light a finite amount of time to travel to us. So when we're looking at galaxies, at these galaxies specifically, we're looking like 13 billion years into the past, which is pretty rad. But yeah, what's cool about this galaxy, so this is from the Hubble image of it. You can see as these 2 little distinct lumps, and they have different colors, and the colors correspond to different types of stars that are in there, or different stellar properties. And I can try and explain. So basically the thing to look at in this graph here is this really bright yellow spot here. So this was discovered on Keck, but using a different instrument, an optical spectrograph. And we found this really strong emission line in there, which is this yellow blip. And that helped tell us exactly where that galaxy is. So basically what's helpful about getting emission lines like this is that you can figure out exactly which emission line that is. And from that, you can determine exactly how far away this galaxy is, because you can map what wavelength you find the emission line at, and use that to figure out. So, okay, wait, let me explain this better. So basically, like I said, everything is always moving away from you at all times. So that means everything is being redshifted. Basically, if you have a wavelength of light, if the space that it's in is being stretched out, then that wavelength will get longer and longer. And that's called redshifting. So basically the light that we see from this galaxy, you see it at a much, much higher wavelength than it actually was in the rest frame, or when it was actually emitted from the galaxy. And that tells us exactly how far away it is. So that's one of the main goals that we have doing spectroscopy, is trying to figure out exactly where these galaxies are by identifying emission lines and figuring out how redshifted that galaxy is. So yeah, this is the one we're looking at now. We're looking for a different emission line than this one. We're looking at slightly different wavelengths.
So Patty,
And if we can get
this
that
emission line is super important, right, for what we do. So this is how we first start finding these objects. And this is something that I did a very, very long time ago with Raja. So now almost 20 years ago at UC Santa Cruz, my job was with Raja was for my senior thesis, was to look for these types of emission lines, but at redshifts of let's say redshifts 3 to 5. So so a little bit closer by, but still more than 11.5 billion light years away. And this is a very special line. This is a line called Lyman alpha, which is, as Patty said, most of the universe is hydrogen. And so a lot of times you're looking for the emission from hydrogen in a variety of different ways. So either in the optical, infrared, through radio, there's lots of different ways to find it. But this is one of the most energetic transitions of hydrogen. This is when a electron goes down from the first excited state to the ground state, and emits this Lyman alpha photon. And we can tell that it's Lyman alpha. So one good question would be, how do you know that these emissions that we see are actually corresponding to a certain transition from a certain element? First of all, it's amazing that the emission that we measure on Earth, you know, we heat up some hydrogen, we put a current through hydrogen, and we can, you know, take a spectrum of that in the lab, and we can measure its emission profile. And we look out 13.2 billion light years to the edge of the universe, and we see the same emission signature, the same exact emission signature. The physics is the same, to the best of our ability to tell. And so we say, aha, that is that line because of a variety of different lines of reasoning. So it's not easy. But one peculiarity about Lyman alpha, because the universe is mostly neutral hydrogen, is that it scatters a lot. So it gets emitted, and then it hits another neutral hydrogen atom. It elevates the ground state electron to the first excited state, and then gets re-emitted into a random direction. And so that re-emission can happen thousands of times. And so that's scattering. So you basically get this halo of Lyman alpha light around the galaxy. The emission from these hydrogen atoms can be removed through dust particles. And this usually happens at the bluer end, so the higher energy wavelengths of Lyman alpha. So the higher energy photons get scattered more often. They run into dust particles, and then they get attenuated or removed. And so you can see this kind of characteristic triangular shape in the line. So Patty has this nice plot up here. On the x-axis is the wavelength. So this is the numerical value of the wavelength. And this is in what we call the rest frame. So this is emitted by the galaxy. So this is unredshifted, deredshifted. And so it corresponds to 1215.7 angstroms, or 121.7 nanometers. So this is bluer than blue. This is ultraviolet, super ultraviolet. But as Patty mentioned, we detect it in the optical. So this is where the redshift comes in. So we're detecting it at really, really red wavelengths. So something around the wavelengths that Raja mentioned being red in the spectrum that he was just looking at. So I think it was maybe 9,800 angstroms, something like that. So 980 nanometers. And so, yeah, so this is rest frame wavelength. So this is emitted by the galaxy. And you see to the left, so bluer, there's a fall off in the amount of light. And then to the right, the redder portion, you can see this kind of characteristic tail. So that tells us that this is the Lyman alpha line, and this is what I was looking for all the time in my senior thesis. And so if we saw that, we're like, hooray, yes, that's definitely Lyman alpha, and we move on. But sometimes it's a little bit more ambiguous. If it's fainter, this is an astounding example, super, super bright, so we're able to tell immediately. But if it's fainter, the noise from the atmosphere, a variety of different sources of uncertainty can creep in, and you have to use other lines of reasoning to be able to tell that this is the line that you think it might be. And so now we have the distance to this galaxy, and so that sets our mathematical equation for any photons that we get from this galaxy. So we know exactly how much any photons that come from this galaxy should be redshifted. And so this is why we can target it now and look for other transitions that are much, much weaker, that don't have these kind of signatures that are very characteristic.
And what is the red line in this? Is that the noise spectrum?
That's the noise spectrum, yeah.
I see. And then black is the sky subtracted spectrum.
Black is the sky subtracted spectrum, yeah. So you can see the residuals.
Okay.
The residuals are not done that great, but we can blame Pipette for that.
I don't know if you've talked about this already, but this thing that's marked Lyman alpha has a distinctly triangular shape. It's steeper on the left and shallower on the right. Have you talked about that?
No, what exactly are you referring to?
So, the Lyman alpha line is steeper on the left side and shallower on the right side of the three.
Yeah.
Oh, yeah,
Yeah.
that's
Yeah.
what, yeah.
Yeah, we
Yeah.
just talked about that.
Okay,
Yeah.
and did you talk about expansion? I mean, expansion meaning this is a result of expansion.
The characteristic shape?
Yeah. Yep.
No, please go ahead. I mentioned some reasoning why that shape would exist, but there's other reasons as well.
Well,
please.
it's tough to explain, but I will just say that the degree of asymmetry, the fact that the left side is sharper than the right side, is related to the speed at which the cloud of hydrogen is expanding. So the material that ionizes the hydrogen also imparts momentum to it. So it sort of creates an expanding bubble, and the degree of asymmetry of that line, the lack of symmetry, actually translates to how fast that bubble is moving out. So that's one of the things you can measure from data like this, from spectra like this.
Yep. So you're talking about like the expanding shell model, Raja?
Yeah, exactly.
Yeah.
Exactly.
Okay. Yeah. So that's kind of the characteristic way that and there's really nice models out there that you can take your profile and you just feed them into this model and you get this nice expanding shell and you get all the kinematics of the gas directly from the profile. So yeah, there's a ton of information contained within this line, that's for sure.
And the asymmetry is caused by this. You have a filled bubble of ions that are emitting, and it's a filled bubble that's expanding. So some of it is moving away from us, some of it is moving towards us relative to the overall galaxy. And that creates a very broad emission line, very broad. But then surrounding that bubble is neutral hydrogen that's being pushed out. And only the part that's between us and the center of that bubble can do some absorbing. The part that's on the far side can't do any absorbing doesn't absorb any of the light that's traveling towards us. And that absorption creates this steep left side, because that stuff is relatively, since that hydrogen is moving towards us, it's blue shifted. So it has a shorter wavelength. So that's what causes this asymmetry. It's a really beautiful phenomenon and remarkably simple. I mean, it's just simple geometry. I have managed to put everyone to sleep with that explanation. Sorry about that.
No, it's great. It's great. No,
over to you guys.
Yeah, that's a really good explanation.
Yeah, and it gets even more complicated than that. I mean, you can have much more complex models because these spherical shell models, they're great, but galaxies aren't spheres, and they can have all sorts of different types of feedback, stellar and black hole feedback, which can cause all sorts of asymmetries in the velocity profile, and you can actually pick those up when you do more complex modeling. So the shell model that Raja just explained, that's kind of the first starting point, and then you can see, Raja, we even did this in Marcine's paper.
Yeah, exactly. Marcine's paper.
Backscattering processes and other higher order velocity signatures in the profile that allowed us to tell a little bit more than just the kind of let's say the rotational velocity or the basic properties of the shell. But even that, it allows you to measure the mass. So if you get the rotational velocity of the galaxy, it allows you to measure the mass, and a lot of other really great information can come out of the Lyman alpha line. The amount of stars being formed, the amount of neutral hydrogen that's surrounding the galaxy. So it's really a treasure trove. The problem is it's one line. And it's usually pretty faint, and so it's really great to have. So one of the virtues of the observations that we're taking now is that, and Patty, this is something we talked about not talking about on this session, but we can talk about it now because we've kind of organically gotten into it, is that we can measure what's called the systemic velocity of the galaxy. So we measure a line that comes from H2 regions, so like singly ionized hydrogen in the galaxy. And so sort of probes the overall velocity structure of the galaxy, and it's emitted from where we think that galaxy is in velocity space. And so when you combine that information with the Lyman alpha line, and the Lyman alpha line gets scattered and perturbed by all the ionized and neutral hydrogen and dust particles that are surrounding the galaxy, you can actually get much more complex modeling because you have a grounding point. You have a way of saying, okay, the galaxy is moving at this velocity away from us using this other line. And then we can use the Lyman alpha line to see what the surrounding gas and dust is doing around the galaxy.
So if you had a contracted shell instead of an expanding shell, it would be asymmetric the other way. It would have a shallow left side and a steep right side. And you never see that. You always, Lyman alpha always this way, shallow on the right side, steep on the left side. The other thing, I don't know if you guys have talked about this. Sorry, I was tuning out sometimes. So did you talk about 2 to 1, like electrons transitioning from level 2 to level 1 already?
Yep.
Alpha. And one of the beautiful things about this is quantum mechanics is a microscopic phenomenon studied in the lab, but the quantum mechanics 10 billion years ago was identical to the quantum mechanics that's going on in our laboratories today. And that's what allows us to decode this light.
Yeah, it would be a really big pain in the butt if that were not true. We would be in big trouble if that weren't true. So I'm very glad that's the case.
I'm going to step away for just a bit. I won't disconnect from Zoom, but I'll be back.
Okay.
Sweet.
And Patty, there was a question in the chat that's been there for a little while by Arjun Khan. Did you want to take a crack at that? I can also chime in.
Let me figure out how to find
Arjun
the chat
asks,
window.
as we know, the cosmic timescale is very large. So we talked about 13.7 or 13.2 billion light years away, all the way to the present day. So how can we study the evolution of the structure of these new galaxies that we're targeting and confirming in the distant universe?
That's a really good question. Yeah, because the hard part is that you can only see a given galaxy at a certain point in time, right? So I guess one way to think about that is that what's nice is that we have trillions and trillions of galaxies at our disposal to look at. So I'm not sure if this is exactly what you were asking. So correct me if I'm wrong, but what's nice is that we can, get information on galaxies at all different points in their evolution, because we have so many that we can look at. So for example, there are nearby galaxies that sometimes we use as proxies for these high redshift far away galaxies, and they're a lot easier to observe because they're closer to us, but they could be at their exact same stage in evolution. There will be some differences, in, let's say, a galaxy that's 100 million years old, that's a billion light years away from us, versus the galaxy that's also 100 million years old, let's say the same mass at 13 billion light years away from us. One of the main differences being that the composition of the universe was so different at those two different time scales, because heavy elements are formed in stars and become more and more abundant as time moves forward. But using, observing galaxies at different points in their evolution across varying time scales is kind of one way that we can look at galaxy evolution. And yeah, I'm not sure if there's something you want to step in with, Brian.
Yeah, sure. So yeah, no, that's a great answer. And yeah, but I mean, I think one really important part of that answer is that we're making an assumption that these proxies, as you call them, so these galaxies that we observe locally are similar in some way to those that are in the very distant universe. And there's various ways that those assumptions may be true, and there's various ways that those assumptions may be false, and we can test some of those, but others are harder to test. So just like if you get a group of humans together and you try to predict their behavior, I mean, the individual behavior of the people is going to matter, right? So for the outcome for this group of people, whatever the task is, the individual behavior of those people are going to matter. But if you start averaging over more and more people, then the outcomes become more and more homogeneous generally. So you start to dampen those individual voices and traits, and it's a little bit of a depressing aspect of human behavior. But in the end, I mean, so you have, the bigger and bigger population that you have, the more likely that assumption, the same outcome is going to happen will be true. And so the same thing goes with galaxies, because there's all these different types of parameters that can affect galaxies. So this could be the environment of the galaxy, the surrounding environment, whether that be other galaxies or that be the gas, the dust, the extended emission called the circumgalactic medium around that galaxy. But also the even larger environment. So like whether it's sitting in a cluster, like the kind of structure that Patty showed in her first slide, or if it's sitting all by itself somewhere else. So even that big mass that's, you know, contained within the cluster that can actually strip out gas from the galaxy and do some other things to transform that galaxy very rapidly. The amount of metals in a galaxy. So by metals, astronomers mean anything that's not hydrogen and helium. So not what you typically think of metals, but anything that's basically not created at the beginning of the universe. There was trace amounts of lithium also in the beginning of the universe, but so anything that's not hydrogen or helium, we call metals. So the amount of metals can change how photons interact with the galaxy. And so whether or not those photons are re-emitted or they kind of scatter throughout the galaxy, so that, you know, gas can either cool or not cool. It's that for how star formation proceeds in a galaxy that can matter. And so getting big samples of galaxies at different stages of the universe. So you know, get this sample of galaxies at redshift 7, which is, you know, 13.12 billion light years away. And you go to redshift 6 and redshift 5. So one of Patty's claim to fame is actually doing this. So taking a sample of galaxies at redshift 6, you're being very modest, Patty. So a sample of galaxies at redshift 6, sample of galaxies at redshift 7, and this is the transition, we think, of this reionization epoch. So when at redshift 7, when the universe was primarily neutral hydrogen, to redshift 6, where the universe was primarily ionized hydrogen. And if you take these, you know, what you think are the same sets of galaxies, it's not that they're not the same galaxies, but the properties are all the same to your best of your ability to tell. So how many stars are being formed, how much mass is in that galaxy, the metals in those galaxies, so on and so forth, the environments of those galaxies. And you can say, okay, we have a population of galaxies here that we think, you know, is more or less the same as the population of galaxies that's a little bit further away. And so the only thing that we're changing is, and we're not changing it, the universe is changing it, is the amount of neutral hydrogen around. And so you can actually probe the amount of neutral hydrogen around and plug that into a model of how the universe proceeds in terms of its evolution, by making a direct comparison between these two sets of galaxies. So that's one way to do that. Another way to do that is through simulations. So a lot of people simulate the universe, and they use observations like the observations we're taking to inform those simulations, and they use those as initial conditions, and then they input physics, and then they forward and back evolve those galaxies. And then we're able to, you know, extract that information from simulations and look and see, are they predicting something correctly through our observations? So they're informed by our observations, but then they're reinformed through new observations. And we, you know, slowly iterate a dance between the people that do simulations, the people that take observations, to get something that's more and more credible, simulations that are more and more credible, that more and more correctly describe the state of the universe at a variety of different ages.
Yeah. You're welcome, Arjun. I hope that answered what you're looking for.
Yeah, it was a great question. It's something we're like, Patty and I both work on this in very different regards, and it's not an easy thing to do.
Yeah.
But yeah, it's very rewarding, and yeah, it's tough, but very fun.
Yeah. Yeah. And that's one of the fun things, I think, not to get philosophical, but like about astronomy and doing the science is you're limited by what you can actually observe, right? So it'd be awesome if we could take one of these galaxies and follow its evolution throughout, 500 million years or whatever, and see what happened to it. But we're presented with the data we can get, so we try and connect the pieces together in the best way we can. And we can also incorporate things like Brian said, like simulations and like physical laws that we know about. But yeah, that's, I think, one of the most fun pieces about this is taking what you can get and figuring out what you can know from that. So yeah, I can stop sharing this. And then we're going to be switching targets in like 25 minutes, right? Or so.
Oh, that's good. Okay, so then we'll have a
Am I
target
gonna-
switch before we officially end this session.
Mhm.
So that'll be the most activity that we have all night. Hopefully, if everything goes extremely well, that is the most activity that we'll have all night.
Yeah. All right.
And Patty, did you want to talk a little bit about the what exactly we're targeting right now, like in terms of like beyond the galaxy, but just like what line we're looking for and why we're looking for it?
Oh yeah, yeah. You mean just like C3?
Yep,
Maybe.
exactly.
Yeah. So yeah, the target of basically this night on the telescope and our last one in January, and we have an upcoming one in July, is all under the same project where we're looking for an emission line called C3, which is doubly ionized carbon. So carbon that's lost 2 electrons. And like we were, thank you. Like we were talking about before, the brightest line in most of these galaxies typically is going to be that Lyman alpha transition. So first excited state of hydrogen down to the ground state. That's the first line that you typically look for when you're doing spectroscopy on these galaxies. But like that DP7, the one I was showing before, once we have that line, if we can get a second emission line, we can get a lot more information out of it. There are lots of different ways you can do that. You can compare the strengths of the two. You can look at what Brian was talking about before, a velocity offset, because the Lyman alpha photons will scatter a lot. So they might be even more redshifted than the actual galaxy itself because they bounced around a lot more within their own bubble before zooming all the way to our telescope. But with the C3 line that we're looking for tonight, it doesn't have that same scattering effect because it's at a different wavelength. So if we can get that line, that gives us what's called systemic redshift, which is the actual true redshift. And if we compare that to how much further those Lyman alpha photons were scattered, that can give us a lot of insight into what's happening in that galaxy. So I think Roger was mentioning before, like figuring out how big that ionized bubble is, because basically as the galaxy is emitting all these photons, it starts to ionize the neutral hydrogen, that's closest to it first, and forms what's called, or the theory now that we're talking about is called like ionized bubbles, where the photons will come out and, they'll carve out an ionized bubble around it. And then that bubble slowly and slowly get bigger until you get the fully ionized universe that we have today. So yeah, that's basically the line that we're looking for, C3. And if we can get that in any of these galaxies where we also have Lyman alpha emission, which is what we're targeting, then we'll be able to get a lot more insights into those galaxies. The ultimate goal would be to get enough to actually, have enough numbers to do statistical kind of analyses on these. But what's also nice is that Brian and I were talking about this earlier today. You guys probably all know about James Webb that launched on Christmas and is now getting all set up and fine aligned and stuff. And these galaxies are some of the main ones that James Webb is going to be targeting. So it's super exciting because James Webb is space-based, unlike Keck now where you have ground-based, you don't have the atmosphere to go through. So we'll be able to get much deeper data on these high redshift first galaxies using James Webb. And the observations that we are doing tonight and in this whole program are kind of like laying the groundwork for those James Webb observations, figuring out which galaxies should we actually look at with James Webb. and we'll be able to get a lot more emission lines with it, which will be awesome. So yeah, sorry, I went off on a tangent there, but yeah, basic gist is we're looking for a C3 emission line to understand more about the galaxies that we think had a big role in reionizing the universe.
And we'd love to look at the same lines that we could get with James Webb. Well, we don't have any time on James Webb, unfortunately. We tried. We don't have any time yet.
Yeah.
But we're gonna try again. We're gonna keep trying. But these types of galaxies are some of the first targets of James Webb for sure. But yeah, one of the things you didn't mention, Patty, is that Lyman Alpha is great. I love Lyman Alpha. There's so much really cool information that you can get out of Lyman Alpha, but Lyman Alpha is a finicky line. It is very finicky, and it can be depressed completely. So it can be completely removed from the spectrum through blankets of neutral hydrogen, or if there's not enough outflow, or there's not enough young stars to ionize the surrounding regions of the galaxy, then you don't get Lyman Alpha in emission. And so then if you want to get it in absorption, which is another phenomenon, you have to integrate hundreds of times longer. And we're already asking for a lot of Keck, doing these 10-hour integrations on these targets. So it's not really feasible to do that. So if we get unlucky with these galaxies, we don't detect Lyman Alpha, and then we can do something with that. That's a lot of our science is having to do with non-detections of Lyman Alpha. And you can do statistical analyses of this and get really useful information on the topology of the neutral hydrogen in the high redshift universe. But we'd love to use other lines, other really characteristic signatures of hydrogen or of oxygen that are always present and are not always present in galaxies that are forming stars, of which most of these galaxies at very high redshift are. We'd love to get these other lines that aren't affected by this scattering process. So this is in hydrogen, H alpha, which would be the 3 to 2 transition, or H beta, which would be the 4 to 2 transition. And these lines are great because they track the number of stars being formed in the galaxy. They don't scatter in the same way that Lyman Alpha does. And these are the kind of lines that we could get with James Webb. And so the question would be, why don't we do this with Keck? But unfortunately, the atmosphere is not only a pain because it blurs everything out, but it prevents us from looking in the mid-infrared, which is where these types of lines. So these are already, so H alpha, for example, is in the human eye. We can see H alpha with our eye. It's at 656 nanometers. And so it appears as reddish. And so it's already red to begin with. And then when you put it in, it being emitted from a very, very distant galaxy, it's far, far, far in the infrared. So much further out in the infrared than we can even see with Mossfire, this infrared instrument that's totally awesome on Keck. And that's because of the atmosphere. So we can't detect these lines. And so there's where you have to go to space. You have no choice but to go to space. But once you go to space and you get a really cool telescope that has, a 6.5 meter aperture, that's, almost the size of Keck, not quite. And since the light collecting power goes as the aperture squared, it's definitely not, collecting as many photons, but you can do this in space. And it's at a particular point in space called L2, which allows it to be very shielded from excess infrared photons from elsewhere. So it's very sensitive at this, and this is our ultimate goal, is to take the observations that we have in the ultraviolet, which we're observing now. We're actually observing in the infrared, but they're emitted in the ultraviolet, and compare that to what we see in the optical with James Webb.
I like how you guys were talking about the full idiosyncrasies of astronomical spectroscopy, why carbon that's doubly ionized is called carbon-3. Did you guys explain that?
Not really. You're welcome to, Raja.
Okay, so it was because back then when they didn't know about the structure of atoms, they saw that you could take a carbon, they saw that you could take particles of carbon and you can make them successively more charged. And the thing that had 0 charge was called carbon-1. The thing that had a little bit of positive charge, the smallest amount you could impart, was called carbon-2. The next one up was carbon-3. So now we know it's because of removal of 0 electrons from the atom is carbon-1 from a carbon atom. Removal of 1 electron is called carbon-2, but it's sort of an arcane system, a spectroscopic system that people had going back to when they didn't really understand the structure of atoms and ions. So that's why you can't have anything more than hydrogen 2, because hydrogen has only 1 electron to give up. So you can't have a hydrogen Roman numeral 3. You can only have hydrogen 1 and hydrogen 2. There's 1 electron. Helium can be 1, 2, and 3. Lithium can be 1, 2, 3, 4, etc. Carbon can be everything up to carbon-7 if you remove all of its electrons. It has 6 electrons. I may have to hop off the Zoom call for a bit, you guys, and then you'll be observing for a bit. So I may just come back on after STS ends just to catch up.
Yeah, that sounds good. You know the Keck I Zoom, of course. That's where we'll be.
That's where you'll be. Okay. Yeah.
Yeah, past 9.
I don't know if I know the Keck I Zoom. I know the Keck II Zoom, but that's okay.
I'll email it to you, rather.
Okay, thank you. Amber, it's wonderful seeing you. I know we're planning to have a chat. We've been meaning to set up a chat with Heather, you, Sam, and Roy, Brian, just to discuss how Shadow the Scientist might move forward, in the future. But I'll email you about that.
All right. Thank you so much.
Thanks.
And thank you for coming, Raja. It was a pleasure.
Hey, take care.
So we have, so Patty, you want to move to our next target? Well, we want to do the Myra starting in about 10 minutes. Is that so?
Yeah. Yeah, I think 12:15, 9:15 your time.
It's already past midnight. How you doing, Patty?
Huh?
How are you doing? How are you doing in terms of sleepiness?
I'm okay. I mean, I slept till 4 p.m. today. So
Oh, nice. Yeah, I saw you were emailing me at like 3 last night. I think 3.
Yeah.
Even 3 my time, which would have been pretty crazy.
Yeah. I slept from like 5 to 8 in the morning because I had class at 9, and then after class I went to bed again. So nice. Thank you.
Yep. So I just took a guess on that. That's crazy. That is crazy. That's the life of a grad student that I do not miss.
Yeah. It's okay.
For a while, if you're young, yeah.
Yeah.
Okay, so 2 repeats are going to put us. Okay, we'll probably be able to get 1 more repeat after this, and then we'll probably move on. Yeah.
Okay. I'm gonna highlight our next target here.
Said you want to do a focus before we start that?
Yeah, is it okay if we in about 10 minutes at 9:15 we wanted to do a Mira, let me double check. Yeah, 2.5 hours ahead of RxJ 1347. I highlighted it on the star list.
2.5 hours ahead.
Patty, are you sure you want to do a Myra? Just as a devil's advocate. I mean, usually we do like 1, I mean 2. If you're making a big move and temperatures change, then sometimes it's worthwhile. I guess we're staying on this target in this area of the sky for a pretty long time, so maybe it's worthwhile. But I don't know. Sometimes it's because we lose like 20.
Right.
10 minutes, let's say.
Yeah. Yeah, honestly, I have no basis for it except that I feel like the way I learned was that you always do a mirror before a new target, but if we don't have to, then
This
And
would be
then
pretty
on
close to where we did the last focus also.
is it? Okay.
Because it's also a southern target. Yeah, and it's
Yeah, I mean, I'm fine foregoing it if you are.
so we're at the same deck more or less. It's just a couple of
Yeah, less
couple
than
of
an
hours
hour.
east. I might do one like when we transition to 1423, just because
Okay.
that'll be,
Yeah,
a little
that
bit more than
one's,
halfway through the night, and then it's also a
Mhm.
higher deck target.
yeah, yeah.
A really big bummer. Chris is on the show road, H1 News, working for Hawaii. An update now on Honolulu Mayor Rick Blanchiardi. Clearing the back.
I got it. So what do you think, Patty? My inclination would be to just keep going through. In which case it may change what you want to do now in terms of switching targets, because there's no longer the 10-minute kind of
Right.
loss from
Yeah,
the-
I guess if we skip Mira, I mean, I don't know, what's like the highest air mass you would go to?
Well, we
target.
can't pick up John, remind me on Keck 1, it's rising targets, right? The Nesmith deck is,
Yes.
yeah. And so that's what, like 38 elevation or something?
Yeah, like 37.
Okay,
So
I'm just gonna check and I observe now, like what time.
but I think
Sorry, it's 34.
okay. So I think we're actually okay, because you were basing this off on 1.5 air masses, Patty? Is that
Yeah,
right? Like yeah.
yeah,
And it's let me check. So you have 2148 is rises above 1.5, so it's probably 1.7-ish at 2115. John, can you tell easily if we're above the 34 limit, even now, I guess?
Yeah, sorry, it's a little bit below 34, and yeah, we could go to the target right now.
oh, we
Okay.
could,
Yeah.
okay.
So why don't we, Patty, why don't we forego the Myra? Why don't we do like maybe another repeat or two on DP7, and then we can end the Shuttle the Scientist with moving over to 1347 around, I don't know, 20 or 25 after the hour.
Yeah, that sounds good. Yeah, that'd be great. Yeah, the more time on 1347, I think the better.
Great.
Cool. Yeah, sweet.
And I was just doing the estimate of the flux by eye. It looks like the traces have broadened out just a bit. Are you running the script to monitor?
Yeah, let me do that right now. Sorry. But remember that this is the mask where it has a hard time tracing the slit star because it's so
Right.
faint.
Yeah.
So I'll try it, but I'm not sure how reliable that'll be.
So that's for the full width half max, is that right? That it primarily has an issue?
Yes, I think so. Yeah. All right. It's taking a considerably longer amount of time to download the data to my computer. than usual, maybe because of the Zoom I have running.
That's okay. I don't think it's going to change any of our decisions, but it was just out of curiosity. We'll get a
Yeah.
seeing estimate when we move over and do the alignment on 1347.
Yeah.
It'd just be good to get a comparison seeing estimate relative to, at least the relative trend could help us because we know the
Right.
initial point when we
Right,
did the
right,
first
right.
observation, first alignment.
Yeah.
It definitely doesn't look bad though.
Sweet.
Exposure complete.
Oh, wow, you have some, there's some bright galaxies on here.
Oh yeah. Yeah.
Magnitude 17 galaxy. The second slip down.
Are you? Oh, you're looking in the mask.
Yeah. Yeah, you know, we're getting continuum on things that are faint continuum, things that are almost 20
Yeah.
first magnitude in 2 minutes. I mean, that is not bad at all.
Yeah, because I remember last time we looked at this mask, you could only see continuing the star and that other galaxy you were just looking at.
Yeah.
Like I don't think I saw any other traces.
Yeah, and this one's 20.8. We're seeing a trace for that. 20.7, we're seeing a nice trace for that. That's great. But let's see for a second. So it's 20, let's see, 20th magnitude, and DP7 is 27.2 magnitude. And we know that 2.5 magnitudes is a factor of 10 in brightness. So it's 7.5 magnitudes difference, which means factor of 1,000. So what's 1,000 times 2 minutes?
1,000 times what?
2 minutes. So if we get 1,000 exposures, we should more or less expect to get similar continuum signal to noise as we're getting for our thing here for DP7.
Yeah.
That seems like a lot. Oh, we're not that far off from 1,000 times 2 minutes. What do we do? Now we're at like 15 hours or something like that for exposure.
We were gonna be, yeah, around 14 hours, I think. I think we have almost 12 now. So
Okay. So
yeah, this isn't.
Exposure complete.
we'll do one more.
Yeah.
And I think I did 2 actually, so we'll just have to abort after that.
Yeah, that's all right.
After the
Because 2 is 4 minutes, right? Because that's 2 nods.
It is 4 minutes, but there's a readout time. So
Right.
it's what is it, 144 seconds per,
Okay.
plus the nod time, but the nod time is like almost instantaneous. So yeah, it's about 5 minutes per repeat.
Okay.
Never tried this abort after repeat button.
What'd you say?
I've never tried this abort after repeat button.
Oh, I don't think I have either.
I think it's time to try it.
Yeah, I've done a board after frame.
Should we roll the dice that the software is smart enough to know?
Yeah, might as
Yeah,
well.
let's do it.
Exposure complete.
You know, I'm not too encouraged by what I saw there. So
Oh,
please wait for the current exposure sequence to abort.
yeah.
Process has exited with the code 0. So we'll see. If it doesn't abort, do you want to just push through? Take an extra 2 times.
Yeah, how
2?
many? Yeah, that's
6.
fine, because we're not even 12:20, 9:20 yet.
You know, like if we're being honest, which is always good to be. And so we were planning on moving to do the Myra 9:15 local time, Hawaii time. And so we, you know, moving it at 25 after local time would be totally consistent with what we would have had during the Myra. So I think that even if it doesn't abort, I think we're totally fine.
Yeah.
But I'm also fine to move if it actually works. Let's see.
Yeah, same. Let me just download these last few. Yeah, so it looks like the I ran the scene script. It does have the same weird differential that it always does with this mask, where the scene, you know, jumps up and down frame by frame.
Yeah.
But
usually one of those is trustworthy. One of the positions, I think it gets messed up by the slit edge.
Yeah, that makes sense.
In one of the nod positions.
Right. Yeah, because one of them is kind of around. Well, no, it seems like the true one, like, because one of them is consistently around 0.4 and the other is closer to like 0.8. So it seems like if we're assuming the correct one is around 0.6, that it's right in the middle.
That would be weird. You can actually go down to the if you share your screen, or actually, wait, I'm sharing my screen. Well, actually, let's see. Well, let's see if this aborts. We have
oh yeah, yeah.
seconds left.
Exposure complete.
That's it, right? The whip.
That's it.
All right.
I'm gonna quick dark.
Yep.
Then I'll let you take over.
All right. So I can set up alignment.
No, I would hold up on that. So, John, we're good to move as soon as the dark's in.
Okay. And
then John,
you can rotate, or you could move the mask.
Perfect. Okay. Thanks.
Okay. Thank you.
And Patty, I accidentally put in, I didn't accidentally, I purposely put in MS1008_V7 because I was looking at the magnitude distribution. So just so you know, it's on that. So don't set that one up. So go on 37.
This guy, right?
Yeah. I should have put it back afterwards.
All right. And we're not doing a mirror, so I can just set up alignment.
Yep.
Cool.
So we'll plan for this to be the last thing that we do for the Shadow of the Scientist session for everybody who's still with us, who was brave enough to stay with us till now. So we're moving targets now. I'm actually, let's share the screen that shows us moving.
Oh, yeah. All right. So I'm good to execute, John?
Yes.
So for everybody who's still sticking with us, hopefully you can see the screen that I just shared. So there's a bunch of different pieces of information here, lots of numbers and plots and everything. On the right-hand side, you can see the guider CCD, which is taking images every couple seconds. And this is showing that we're moving to a different target. So the streaks that you see going across are either stars or galaxies or atmospheric junk that we're passing through. And the scroll bar that's on this FACSUM window here is kind of status bar to how long until we arrive at the location that we're trying to go to. So John's moving the telescope for us right now, and we're about 85% of the way there from our previous target to this target. And you can see these numbers changing pretty rapidly. This current alpha and delta, these Greek letters alpha and delta. So this is right ascension and declination. See it actually, oh, I didn't even know that it did this. That's cool. So current right ascension in hours, current declination in hours. So this is degrees, arc minutes, arc seconds. And so we've now arrived at this target, and this alpha and dec are the points on the celestial sphere. So just think of them as alpha would be longitude, and delta would be declination, would be latitude. And so just take the latitude and longitude of the Earth, and you expand that out into the sky, and that creates the celestial sphere. And so at every point on that sphere, we can specify a location in terms of these two coordinates. And so our next target is at this specific set of coordinates. And so John got us.
You're good to start alignment whenever you're ready.
Great, thanks.
Thank you.
Got us very, very close. And maybe even right on, but we're going to check right now to see, well, actually not right now. We're waiting for something to happen before we're able to check, but we're going to check and see if we're at the right location. So what we're doing right now is we're actually reconfiguring the spectrograph. So the spectrograph creates these little slits, as we talked about before. And normally with a multi-object spectrograph, you have traditionally you have a piece of metal, and you cut out the slits in that piece of metal. So you use a laser milling machine to cut out slits in a piece of metal, and then you stick that piece of metal in the optical path. So meaning in between the telescope and the detector, whatever you're using, and that sets the location of those slits. But MOSFIRE is really, really cool, and James Webb uses the same kind of technique, where there's these set of configurable slit units. So they're just basically bars, and this is in a cryogenic environment, and they move like this. So if you can see me moving, my arm's moving. So you have a bar that moves in this way, a bar that moves in this way, and it creates a slit in a particular location. And you do that for all, I think there's something like 50 sets of, how many are there?
Yeah, 92 divided by 2. Whatever that is.
Whatever that is, yeah.
46.
Yeah. So I'll share that one. Let's see. So we're moving things right now. And so these different, Patty, you can actually do the go dark imaging J.
Oh yeah.
No.
Oh, fuck.
Yeah, so it's dark imaging J. Yeah. So yeah, don't click anything now. It's okay. So you can see it says target J. So we actually might get some persistence from this, which will be unfortunate, but hopefully we're going to get like, okay, quick dark. Can you do it? Or you can click.
Yeah, I clicked it.
Dark imaging J also could maybe do it, hopefully. Yeah, this is, if you click the wrong button. Okay, go ahead. Quick dark or dark imaging, either one. Yeah. Okay, we should take a look out for, so we'll see this in our alignment image. We'll see if there's any persistence. So what Patty and I were just worried about is that, so as these slits are moving, these bars are moving, basically one opens and then the next one closes to meet it. And so you expose the detector to light, and actually because it's infrared light, we have to put in these filters that block infrared light. And Patty accidentally clicked one of the buttons, there's tons of buttons, it's super easy to click the wrong one. And I bet you got fooled by the thing that says like dark image up at the top.
Yeah.
And so you're like, oh, that's a safe place to click. But actually what that did was put in this J filter, so it actually exposed the detector to light. And so if it so happens that when you're opening up these different slits and there's a really bright star or something like that, there, the detector is naked against that. So it's exposed fully to that really bright source, and that can leave an imprint that's really bad on the detector for us that can persist. So it's actually called persistence, that can persist for a long time in our observation. So luckily, Patty, our primary targets of interest are not near our stars. Hopefully the stars, there weren't other stars, bright stars, where our targets of interest were. So at least if something gets, if there's persistence, it'll be away from our really important science objects. But we'll see in a second if that's the case. So yeah, in any case, so we're moving all these CSUs, these configurable slit units, and we just did it. And so now we have a mass that looks like this, and all these green things are the slits and boxes. So we're now going to look through. So why don't we do a course line, Patty?
Okay. Guider.
Yeah, and so I'll share that screen. Oh, you don't need to query DSS every time. You can
Okay, just grab guider.
Yeah, and then you grab guider image. That was pretty good. I wouldn't even move it. So I would just go to final line.
Okay.
And then I would just start the final line. So now we're going to take an observation, and we're going to undo the process that Patty just did, which was we're going to put in this J-band filter, which allows wavelengths of light that are, let's see, in nanometers, about 1100 nanometers, something like that. So 11,000 angstroms. And we're going to let in those wavelengths of light. And we're going to take a image through this new set of slits and boxes that we have created with this configurable slit unit mechanism. And we're hoping to see the stars that we have, 5 different stars that we have that we're expecting to fall within these boxes. And if they all show up in the right locations, then we're happy. And that means that the pointing is where it should be. And if they don't show up in the right location, then we need to move the telescope slightly to make sure that we get them in the right location.
Is it going?
Doesn't look like it. It looks like it failed.
Just
It
press
says
again.
error, final line failed. So what you can do is I would actually exit out of this.
Out of this whole.
So file, quit, and then you can start the thing again. So this would be a slow mask alignment tool. Yeah. Sometimes IDL just crashes.
Okay. So you can just do final line.
Yeah, just do the final line again. There it goes. Yeah. Sometimes you just need to kick it. Yeah, and actually, Patty, if you see down at the bottom left of that screen, there's like the little thing that says Silver line, and it should have like the IDL window. So if you click that, probably will bring it up. Yeah, so this might be the old one, but in any case, so like you can tell when it starts to fail by opening up these windows.
Okay.
It'll give you some error messages that don't look good, like that. Exactly.
Okay.
So set obs mode, error.
Yeah.
Error moving motor. So it just basically lost the connection to the.
Okay.
I don't know what they call it at Keck, but to basically tell the
Exposure complete.
the configurable elements to change. Okay, Patty, can you zoom out here a little bit and change the stretch? Okay, that actually looks pretty good. To change this, no. We just took a sky exposure. So I'm just looking for persistence.
Okay.
So we might have, I don't know. You mind if I take over for just a second?
Yeah.
So I bet you that's persistence there.
Oh shoot.
So it's just, you see these features. This is like basically, it's darker. So I don't know. I don't know what the level of this is relative to what we would expect, just kind of like the RMS variation. But it could be that that's the signature of persistence. Okay. But luckily it's far enough away from our science stuff, which is our real science stuff, which is down there.
Exposure complete.
Okay.
I'll back. That doesn't look good.
No.
I can see some stars though. So why don't you take a look at the there and see if you can see some. And you probably want to do scale min max.
Okay.
There you go. So you
It's
see right
there.
on the edge there.
Yeah.
I would just do a quick. I would just do the course line. We're just right on the edge. So
Okay.
let's try that. But usually when you do the course line, Patty, you do the select target first. So go to select target, which is no, just down there. Current RA deck, you see.
Oh,
Do your favorite query DSS button.
right.
And
Okay,
then grab your image because it doesn't know which target you're looking at.
right. So I haven't done course.
No, it's all good. And then just, it looks like it's pretty good, but just click on, I would take the brightest star. So that one, yeah, and click on the white box. And it's just a tiny move there, but I think probably enough to help us get in the box. So, yeah. And then, good. Okay, then go back to final line and then do what Shenshu told us last time exactly. And send moves and retake image, because what this does is it saves us time because we don't have to go ahead and click on it.
Okay.
We don't have to take a sky frame. So basically, we've already taken a sky frame because we weren't on the stars.
Okay, yeah.
We're totally fine. So it knows to use the first image in that sequence, which is it moves off of the where the star location is. So it's just, random location in the sky, which hopefully is blank.
Exposure complete.
Okay.
That looks much better.
You want to retake?
Oh, definitely. But so you have a couple ones that are
Yeah, the X is off for all of them.
X is off by quite a bit, and that's the squatter part of the box. But yeah, why don't you send moves and retake image, and we'll hope that it gets okay. Yeah, and you can see that it's really just right at the edge there in the DS9 window. So the Centroid won't be very good for those. So for everybody who's still with us, we're just making slight movements. We're trying to get these, we're trying to do exactly what we just did. So get these stars centered right in the boxes. Now we have a small movement X, Patty, and that's a residual from us not being able to centroid very well the first time. You see the offset is -0.12 and the threshold is, so I would say send moves only. So just say, oh, no. Sorry, did you just do that?
Yeah.
So you said send moves only?
I did, yeah.
No, that was my fault. I didn't notice that there was a rotation. So why don't you click no on all of them? And then send moves retake image. And I hope that it's gonna. No, it's my fault. I hope that it's gonna remember that we have a first image.
Exposure complete.
Oh, it almost looks like it was taking an exposure while we were moving. That's funny. Anyways, we're there.
Okay.
That one profile looks kind of fat, but that's okay. Yeah, we're good.
All right. So quick dark.
Yep.
Yeah, set of science. Is that cool?
Yeah, we're at a good, we don't have a choice, but we're at a good angle.
Should I wait till, okay. Am I good to execute?
You are good to execute.
And base is marked.
Thank you.
Thanks, John.
Forgot about that.
Yeah, I know, a lot of action after
Yeah,
after
sorry
2.5
about
hours
that
of doing nothing.
button. That's my worst fear, is pressing the wrong button up here.
Yeah, it's helpful to just take a second before you click a button. I know it's like it's really easy to misclick, and like yeah, even if you hear me say like do something, I'm an idiot a lot of times, and as the night goes along, like I'm gonna be more and more of an idiot. Which I'm sorry to leave you at like 6 a.m. your time when like idiocy is at its peak, but
That's okay.
but yeah, so just to take a second, like, okay, are we sure that's what we want to do? Because, you know, sometimes that extra half second to, you know, a couple seconds can save you a lot of misery.
Yeah, yeah.
We got really lucky actually that there was no bright sources. I don't think.
Yeah, it's probably a good time to update your exposure control.
Oh yeah, yeah. Good call. And everything else should be the same. 1.25.
Yeah, you can also put in your dark spectroscopy. Are you going to observe in H-band?
Yeah, we're gonna do H-band.
Yeah, so you can put in a dark spectroscopy H.
Yeah, perfect.
I'm just gonna do increments of 12 again, at least for now.
Yeah, sounds good. Okay, so for everybody in Shadow the Scientist still here with us, so this is going to be the last thing that we're doing. So we are centered on our last Shadow the Scientist target, and so this is a new cluster called RxJ1347. Patty's just finishing up moving all the CSUs, so all the configurable slits.
All right. We good to H and wait and go?
And then you're good to put in, so yeah, H is good. And then wait and go. So we're moving the filter into the location where we can expose the detector to light. And then we're going to do exactly the same thing that we were just doing with the previous target. We're going to observe for many, many hours, nodding the telescope back and forth. And we're going to hope for a few photons from the distant universe to get to our detector and tell us about some very distant galaxies. So I think this is a good ending point for Shadow the Scientist for tonight. I think let's see, there's another session that Raja's running in early May, and then Patty, I know we'll be back in July.
July 10th.
Yeah, and then I'll be hopefully running one on Gemini or multiple ones on Gemini sometime this summer. And I think we're gonna be also using the Subaru telescope coming up in the winter time. So there'll be plenty of other opportunities for people to come on and enjoy very distant galaxies or very close by galaxies or everything in between. So thank you everybody for joining us, and thank you to all the observatory staff for coming along for the ride. And I think we'll move over now to the official observatory Zoom. Patty, Chenshu, and John.
Perfect. Thanks for coming. Bye-bye.
Thanks everybody. Good night.